All right, welcome everybody to today's Schubert seminar, where we are very happy to have Matt Larson from Princeton speaking. Before the title, let me just announce that towards the end of the semester, something like late November, early December, we expect to have some early career sessions. So please send us some nominations. Right? You can nominate your students, you can nominate other early career people, you can nominate yourself. We are happy to get all the nominations we can get for nice talks. And other than that, let's continue with today's talk by Matt Larson, who will tell us about fine Schubert polynomials. Yeah, please go ahead.
I'm going to talk about Schubert polynomials, which are something that Daoji and I introduced in this paper that came out last year, I guess. And the main application of them is that they give you some additional control over Groebner degenerations of matrix Schubert varieties. So I'm going to start by talking about Groebner degenerations, maybe in a very kind of general setting. So the basic situation with Groebner generations is that you have some algebraic variety, or it doesn't really have to be irreducible or anything, just some subset of C to the n where X is the vanishing locus of an ideal, and here the ideal in the polynomial ring C adjoin A1 through AN. Okay. And so if we choose some weight W in Z to the n, then that gives us an action of C star on C to the n via some number T in C star on some point A1 through AN in C to the n is equal to T to the W1. So maybe W is equal to W1 through Wn times A1, T to the Wn times AN. So just scaling the coordinates. Okay. And then the reason to consider this is that it's interesting to consider what happens to X as we act by this copy of C star and then send T to 0. Okay, so we're going to look at the limit as T goes to 0 of T dot X. Okay, so let me explain what this means, because it's not usually you don't take like the limits of sets. It's not like calculus students don't. So one way to define this is that you consider the set of pairs TP T in where T is in X and T is in C star. So this is contained in C to the n times C star. And then you can compactify C to the n times C star to C to the n times C, where you just add like an extra point over 0. And you can take the closure of this set inside C to the n times C. Okay. So just the closure of the same set. And then C to the n times C has like a projection, maybe I'll call it P to C. And then this limit equals to 0, T dot X is maybe defined to be the inverse image of 0. So it's at least as like as a set, what it is the set of points that you can obtain inside C to the n by choosing like a sequence of points in T dot X for each T is like T goes to 0. But then there's like some scheme structure, so it might be non-reduced, there might be some multiplicities. So usually it's kind of not that easy to compute what this thing is. So I will also call this in WX, or the initial degeneration of X. So let me explain what the algebra problem is when you need to, for what computing in WX is in terms of algebra. So suppose I have some polynomial f of a1 through an um, in I. So I is the ideal corresponding to X. Then I can cook up a polynomial which which vanishes on this closure as follows. So to do that, I'm going to cook up a polynomial which vanishes on this set first. So if I consider the polynomial f of t to the minus w1 a1, t to the minus wn an, this vanishes on the set of things of the form TP T, where T is in C star and P is in X. And then I can this polynomial, it doesn't really extend. It might not extend over to define a function on C to the n times C, because there might be, when you write it out, there might be a bunch of copies of like T inverse in there, which is not defined at 0. But you can multiply through by some power of T, and then you to sort of clear the denominators. And if you multiply through by the least value of T that you can, then you will get some polynomial on C to the n times C. And when you set T equal to 0, you will get something non-zero, some non-zero thing which vanishes on this initial degeneration of X. So, so clear denominators in a minimal way. And then set T equals 0, and you get some polynomial, which I'll call NWF. So concretely, this is the NWF is the monomials of F. Like what you do is you look at the monomial expansion of F, and then you take the monomials that have the largest W weight, and you set all the other monomials to 0. Okay. And then one can show that the ideal of NWF is, of NWX, so this initial degeneration of X, this limit, is equal to the ideal generated by NWF, where F is in your, the ideal of X. Okay? So, when you're trying to understand what this initial degeneration is, or at least, what its ideal is, what that amounts to is, computing what this ideal is. And we say that F1 through FR is a Groebner basis with respect to W, or W, if the ideal of NW of X is generated by NW F1 NW FR. Okay. And we say that they are a universal Groebner basis if they're a Groebner basis with respect to every W.
And so it's some non-obvious fact that universal Grosvenor bases exist. So the fact that given a weight W, there is a Grosvenor basis, that's just like a consequence of the fact that the polynomial ring is Noetherian. It's some ideal, and so it's finally generated. And so, I could choose a bunch of, generators, a bunch of polynomials such that their initial terms generate. But the fact that there's a universal Grosvenor basis is a significantly deeper fact. So what is true is that there are sort of finitely many, there are infinitely many choices of W in CDN, but there are only finitely many possible in W of X that occur as you vary W. And then, I think that the proof of this, like, it's like maybe the most transparent proof, at least, uses like the existence of the Hilbert scheme or some sort of deepish fact from algebraic geometry. Okay. Okay. Any questions about Groebner bases? So yeah, maybe I should say that the main reason, one of the reasons why one would want to, identify the Groebner basis for some ideal or understand the initial degeneration is because X may be very complicated. Polynomials in general are very complicated. But then once you take this initial degeneration, often um, often this is a monomial ideal. So often if W is sufficiently generic, then this will be generated by in W of F for some F in I where in W of F is a monomial. And then monomial ideals are essentially, they're also kind of complicated, but they're essentially combinatorial objects. And so whatever you want to compute could be, you can at least try to relate whatever you're trying to compute for X to something for in W of X. So, for example, you might hope, and this is true under some hypothesis anyways, that the dimension of X is the same as the dimension of in W of X. Okay, so
silly question. If W is not generic, then probably you don't have a term order. You don't have a total order on the monomials. So does that mean you still have a Gröbner basis in the usual sense if you refine your term order?
yeah, so so if W is not generic, then yeah, as you say, usually the initial ideal will not be monomial. But you can kind of this definition of the Groebner definition of Groebner basis I gave, maybe not what you would see depending on what book you look in, because maybe they're assuming W is generic or you have a term order. But it still exists for general Noetherian reasons, and furthermore, trying to understand a Grosvenor basis, what Grosvenor basis for non-generic W, it kind of immediately reduces the case of generic W because again, it's not obvious, but it turns out that if you look at in V of in W X, this is equal to in W plus epsilon V X for epsilon sufficiently small. And so if you want to understand a Grosvenor basis, like you want to understand what happens when you degenerate with respect to W, then you want to sort of understand a Grosvenor basis or something. This fact implies that if you have a Grosvenor basis for W plus epsilon V, then it will also be a Grosvenor basis for W. And so, if you could choose V generically, then this W plus epsilon V will be generic. And so,
Okay, thanks.
okay, so in the Schuberty world, there's some community of people who think a lot about Grosvenor bases and proved a lot of great theorems about Grosvenor bases. And so maybe at least a lot of the work has been done for a type of variety called a matrix Schubert variety. These varieties were introduced by Fulton in the 90s. So, okay, so one way to define them is that there's a map from GLN to GLN mod B, which is the flag variety. So maybe I'll call this P. And inside the flag variety, there are these Schubert varieties, called them YW maybe. So I will describe what my conventions are later. And maybe I'll call them Y pi. In terms of like upper triangular versus lower triangular, but and in any case, there are there are these Schubert varieties here, and there's also an inclusion of GLN into an affine space, into C to the n squared. And then the matrix Schubert variety of pi is the closure inside affine space of P inverse of Y pi. So here pi is a permutation. So this sits inside matrix space, which I'm thinking of as C to the n squared. Yeah, and my convention is that the dimension of x, yeah, so we'll call this x pi. So x pi is the matrix Schubert variety. My convention is the dimension of x pi is equal to n squared minus the length of pi. So the length of pi is the codimension of x pi. Okay, and then there are some great theorems about the Groebner degenerations of matrix Schubert varieties. So the first theorem from the 2000s, due to Knutson and Miller, is that there is some W in Z to the n squared, lowercase n, such that in W, x pi is a union of coordinate subspaces, union where the coordinate subspaces are indexed by some combinatorial objects called pipe dreams. And in particular, it's reduced. Okay, so there's some combinatorial object called a pipe dream that is associated to pi. And there is some straightforward way to take a pipe dream and construct a coordinate subspace of C to the n squared using that. So by coordinate subspace, I mean it's like given by some of the coordinates are 0 and some of the coordinates are allowed to be anything. And so what they show is that for certain W, so there's some explicit condition, then when you initial degenerate x pi with respect to that W, then you get a reduced union of coordinate subspaces, and they say like exactly what happens. So exactly what the definition of a pipe dream is will not be super important, but okay, so they just completely describe the degeneration. So the second theorem is more recent due to Klein and Weigand. So they show that there is some W in Z to the n squared, such that the initial degeneration with respect to their W, and again, it's some explicit thing, is a union of coordinate subspaces with multiplicity. So the limit is not reduced in this case, given by bumpless pipe dreams. So again, some, combinatorial object, bumpless pipe dreams. Yeah. So in this case, they don't say, yeah, they have some recipe which takes a bumpless pipe dream and produces a coordinate subspace, but different different bumpless pipe dreams for the same permutation can give you the same coordinate subspace. So maybe there's some coordinate subspace that occurs like 17 times or something. And they don't know exactly what the initial degeneration looks like, but they know that it's a union of a bunch of coordinate subspaces, sort of exactly those given by the bumpless pipe dreams. And this particular coordinate subspace that occurs for 17 different bumpless pipe dreams, that one has multiplicity 17. So basically, they know at least roughly what the degeneration looks like. Okay, and so this has some sort of topological consequences or topological for the matrix Schubert varieties. So you could compactify c to the n squared by p to the n, pn to the n. Yeah, right. So an is a subset of pn, or yeah, c to the n is a subset of pn, and then you just sort of take the product. So you're projectively completing the rows. And you can consider well, the inside here I have xw, and inside here I can take the closure x pi. Sorry, x pi. I can take the closure of x pi in here, and I can consider the fundamental class of the closure of x pi in the homology maybe of Pn to the n. So I get some class in the homology of Pn to the n. And yeah, so what's true is that the homology class, so yeah, basically because x pi is cut out by appropriately homogeneous equations. The if you look at the what happens, so you can there's an action of, I chose my weight W, and there's an action of C star on Pn to the n, which compactifies the action of C star on C to the n squared. And you can degenerate x pi inside C to the n squared and then take the closure, or you can degenerate the closure of x pi in Pn to the n. And then, yeah, a priori, these are kind of different things, but because of this sort of, x pi is sort of homogeneous in the appropriate sense, you get the same thing. So, what the consequence is that if I take the closure, the homology class of the closure of the initial degeneration is equal to, right? So this is the initial degeneration is a subset of c to the n squared. And I take the closure, I get something at pn to the n squared, and that is equal to the homology class of the closure x pi. But this is in either the Knutson and Miller or in the Klein-Weigand setting, this is a union of coordinate subspaces, possibly with multiplicity. And so what we get is that we get a formula. Yeah, for a union of coordinate subspaces, it's very easy to compute what the homology class is. And so we get a formula for this thing, for the class of the closure of x pi in the homology of the product of Richard spaces. So we the corollary is that this homology class, it's equal to the class of the Schubert polynomial of pi evaluated at, so this hi is like the hyperplane from the ith factor. I guess the first factor. Yeah. Okay, and then you cap with the fundamental class of Pn to the n. Okay, so the proof is that the Schubert polynomial has an expression in terms of bumpless pipe dreams or pipe dreams. Yeah, bumpless. Yeah, so as far as I know, this fact was maybe first proved in Knutson and Miller using this sort of Groebner degeneration argument. And so then you could deduce, but you should think of the either the Klein-Wygant result or the Knutson and Miller result. Well, yeah, one way to think about it is that it kind of explains why there is this formula for the Schubert polynomial in terms of pipe dreams or bumpless pipe dreams. So like from the definition of the Schubert polynomial, it's not so transparent, for example, that the coefficients are non-negative, but then you could prove, combinatorially that they count something, they count pipe dreams or bumpless pipe dreams, but then this gives like a geometric explanation for why they count something. Okay, so let me say that the one upshot here is that in these two works, they proved something about algebra, about Groebner, degenerations. And the way I'm presenting it, you can use that to deduce some sort of topological information. So the way the proof actually works is that there's sort of more of an interaction between that. So you sort of prove something about topology, and then that gives you some, sort of handling of the Groebner theory and how the initial degeneration looks, and then you can use that to deduce something else about the topology, like what the fundamental class is. But somehow there is a very tight connection between the Groebner theory and sort of the topology of your subvariety or your closure in some product of projective spaces. And then the reason for that tight connection is basically because the initial degeneration is preserved or the homology class is preserved under degeneration. And so you know that the degeneration will sort of share this topological properties with what you started with. And so maybe just one philosophy is that if you have some subvariety X and you're trying to figure out what the initial degenerations are, then you could try to write down a bunch of equations for your that vanish on X. So you write down a bunch of elements of your ideal, and then you take their initial terms, and then that gives you something which vanishes on the initial degeneration. So that gives you like an upper bound. You can use that to deduce that some point is not in the initial degeneration. But just from sort of thinking about the algebra alone, it's often difficult to produce like a lower bound on the initial degeneration. Like, okay, so you sat down and you wrote down polynomials for 30 days. How do you know that you actually have written down enough polynomials to cut out the initial degeneration? And the way you usually get a lower bound is using topological information. So that gives you some sort of lower bound on the. And so, often when people prove theorems like this is a Groebner basis for whatever ideal, often how it works is that they write down sort of the obvious polynomials, and then they produce some sort of topological lower bound, and then the bounds match. And so then you know sort of what the initial degeneration is. Okay, yeah. I think maybe this is a good time to take the break unless there are questions.